Okay, so we're in part 2 of section 2.2 and 2.3. This is a continuation of the last video. We just gone through the steps on solving a linear equation in one variable, and we're going to take a look at some more examples that are slightly more advanced, and then finish up with some translation problems. So in this example, we're just told to solve again, and now we have a mix of distributions and fractions. And now in the last set of examples in the last video, we found common denominators and solved with the fractions. Now I want to show you how you can eliminate the fractions altogether. So we're looking at our denominators here, and we want to find the least common multiple of all of them. So every fraction you see, you need to take into account. So the least common multiple of 2, 2, and 8 is 8, because they all divide into 8. So I'm going to multiply this whole side of the equation by 8, and I'm going to multiply this whole side of the equation by 8. So this 8 is going to get distributed. Now this looks like it should be distributed, but since this is multiplication right here, this actually only gets multiplied once to the 1/8, because it's multiplication and multiplication, whereas this has the subtraction symbol. So if you're ever wondering, do I need to distribute, remember the main operation that's connecting our two terms, and yes, we're going to think of this inner parentheses as one whole term, is multiplication, which means we don't distribute, because this 1/8 is already needs to get distributed to both. So this 8 is only going to get multiplied by the 1/8. 8 divided by 2 is 4. And then we have x plus 5. 8 divided by 2 is 4. And then we have x. So that's the left side. And the right side, 8 times 1/8, or 8 divided by 8 is 1. So we just have 15x plus 3. So now we've gotten rid of the fractions. Now, an important thing to remember here is even though the fractions are gone now, our answer may still have a fraction. So we get rid of the fractions instead of, like we did in the last video, working with fractions, because it makes our life a little bit easier in this step. So now I need to distribute the 4. We have 4x plus 20. 4 times x is 4x. 4 times 5 is 20. Bring down the plus. Minus 4x equals 15x plus 3. So now we're going to simplify. We're in step 2 here. We did the distribution, and then we need to simplify both sides. So we do have some like terms. 4x minus 4x is 0. So this becomes 20 equals 15x plus 3. Now we're into step 3. We're going to use our properties of equality. So I'm going to subtract 3 from both sides. I have 17 equals 15x. And then I'm going to divide both sides by 15. And we have x equals 17 over 15. And here again, as I said, even though we got rid of fractions in this step, at the end our answer still had fractions. And then the last thing to do would be to check the work, plugging 17 over 15 back in. And so I'll leave that for you to check, but it will work. It's good practice to try it out, so I recommend that you do try that out. So now, moving on to the next example, we have decimals again. And the purpose of these new examples is to be a little bit more challenging. So notice here we have 0.02, 2.7, 0.1, and 0.3. So the left side only needs 10 to be multiplied by 10, both of these, to move that decimal place once. But on the right side, if I only move the decimal place here once, I'm still going to have a decimal. So we need to move it twice, which means we need to multiply this side by 10 times 10, or 100. And whatever we do to one side, we need to do to the other. So we need to multiply by 100 on both sides. So we are going to move this decimal place twice. So this becomes 330x plus 10 equals 270. X minus 1, 2 is just 2. So we have made the numbers bigger, but not much more difficult, because our values are all just multiplied by 10. So we're going to add 2 to both sides, and at the same time I'm going to subtract 30x from both sides. because there's no simplification on the left and right individually like there was here. So 30x minus 30x is 0. 10 plus 2 is 12. 270x minus 30x, it's really 27 minus 3 because the zeros just add a 0. So 27 minus 3 is 24. Bring our 0 and our x down. 2 minus 2 goes away. And then we're left with 240x equals 12. We need to divide by 240. Divide by 240. And we get x equals 12 over 240, but we're not done because 12 goes into both of these evenly. So 12 divided by 12 and 240 divided by 12 gives us 1 over 12 goes into 24 twice with a 0 remaining. So 1 over 20. So again, even though we got rid of the decimals and made everything whole numbers, our fraction or our decimal still appeared here. And to check our work, we'd use some calculator assistance. 1 over 20 does have a nice decimal representation at 0.05, so your answer could be either of those, unless it asks specifically for a fraction. And again, our next step would then be to take this and plug it back into the original. I'll leave that to you to try. It will work, I promise you, but go ahead and try that out on your own. We're going to continue on. I have 2 practice problems that are very similar to those 2 that we just did. So you can work on those. And again, you're just trying to repeat the steps. So these are a little bit more challenging than the last video was. They're going to require a little bit more of you, just like the last 2 examples. These 2 examples are some special types of equations. So this is what we call identities and equations with no solution. So we're going to just start these as we would any other. First one, distributing the 3. So we have 3x plus 5 equals 3x plus 6. I want to move my variables to the left, so I'm going to minus 3x. I'm going to move the numbers to the right, so I'm going to minus 5. Everything from both sides. 5 minus 5 is 0. 3x minus 3x is 0. 6 minus 5 is 1, not 6. And then 3x minus 3x is 0. So now we have 0 equals 1. Well, this isn't true. This is false. So what this means is that there are no solutions. Whenever you come to a result that is false, 0 equals 1, 2 equals 7, something like that, it's never going to be true. 0 will never equal 1 no matter how hard we want it to. So that means that there will be no solution to these 2 equations. Or to this one equation, I should say, or this expression, 3x plus 5, will never equal 3 times x plus 2. It can't happen. So this is how you will know that you have no solutions, when you get to a false statement like this, 0 equals 1. So that's no solutions. This next one, again, start out normal, distribute the 6. So we have 6x minus 4 equals 2 plus 6x minus 6. I can collect like terms. 6x minus 4 equals 6x minus 4. Now, you may be noticing something interesting. 6x minus 4 definitely equals 6x minus 4. So we'll come back to this in a second. But let's say we continue on. I want to move my variables to the left, my numbers to the right. I'm going to minus 6 from both sides. I'm going to add 4 from both sides. 6 minus 6 goes to 0. 4 minus 4 goes to 0. 6 minus 6 goes to 0. 4 minus 4 goes to 0. 0 equals 0. Well, the result here is this is true. Right? This is always true. And even up at this step right here, this is true. Something always equals itself. 0 always equals 0. So you can recognize these types of equations if you get something equal to itself. 6x minus 4 equals 6x minus 4. Now, if you don't recognize it at that point, you just keep working like we normally would, and eventually you will get to 0 equals 0 in these types of cases, always. When you have this, this means that it's always true, and so that means there are infinite solutions. Because 0 always equals 0 every time we want it to, which means that 6x minus 4 will always equal 2 plus 6 times the quantity x minus 1, no matter what. So these are our two special types. This is what we call an identity. And it's called an identity because it is identifying itself in a new expression. 6x minus 4 is the same as 2 plus 6 times the quantity x minus 1. It's identifying another way to write itself. And identities are a big part of mathematics. We constantly look at identities. Every formula that you know that we'll be studying, so things like the distance formula, those are identities. Distance is recognizing or identifying itself as rate times time. And then this one here is a false statement. It is a no solution. So we want to be able to recognize these, and you'll always be able to recognize them by your final result. You'll have a false statement like 0 equals 1, or you'll have a true statement like 0 equals 0. Infinite. Didn't finish that word. Infinite solutions. Okay, so our final example here is an expression. Now we're actually not going to find the three numbers. We're just going to translate this, and then in a later section we're going to find what those are. So three numbers such that the second number is 3 more than twice the first number, and the third number is 4 times the first number. They tell us the sum of the three numbers is 164. So when you're trying to translate problems like this, the first thing you want to do is identify what you're looking for. So we're looking for 3 numbers. So we need to give those numbers names. And this means variables. It doesn't matter what variable you choose. Traditionally, I pick x, y, and z. You can pick a, b, c. You can pick t, u, v. You can pick q, w, and p if you want to. It doesn't matter what 3 numbers, what 3 letters. And then just identify what's your first, your second, and your third. Because they're telling us information about the second number, and the third number, and the first number. So our first number is x, our second number is y, and our third number is z. So the second number is 3 more than twice the first number. So our second number, y, is the way we say equals in English without saying the word equals. So 3 more than. More means plus. So we have 3 plus more than twice the first number. Twice a number is double or 2 times. So y equals 3 plus 2x. The third number is 4 times the first number. So the third number for us is z. This is 4 times, that one's pretty self-explanatory, 4 times the first number, x. And then the sum of the 3 numbers is 164. So x plus y plus z equals 164. And if you want to add a final equation, since they don't tell us about the first number at all, we get to assume it's just itself, x equals x. So in a later section, we're going to then look at this example again and how to solve this, how to figure out what those 3 numbers are. But for now, we're just getting practice translating again. So for this practice problem, Don't worry about finding the three numbers. Just set up all of the equations, all of the expressions that they're telling you from this information. Okay. And this is the end of 2, 2, and 2, 3.